Hey guys, it's Sathija Monagay, Kelly Shen, and Sophia Skoskev, and today we're going to be discussing reflections in plane, concave, and convex mirrors.
Alright, so light is the smallest quantity of energy that can be transported. A photon is an elementary particle without a real size that can't be split, only created or destroyed. Photons behave as both particles and waves, resulting in ability to cast virtual images onto objects due to their wave-like nature. This phenomenon is known as a reflection. Reflections are encountered every day by most people, whether it is catching a quick glimpse of yourself through a tinted window on a sunny day, or looking in a mirror as a portion of our daily routine. Reflection is the change of the direction of light as a result of coming into contact with a different medium, and it comes in two forms: specular and diffuse. Specular reflection maintains the original image and is seen in objects such as mirrors. Diffuse reflection retains the energy of the initial ray of light, but not the image, and is seen in lamps and other lustrous objects. The difference in between the two is that specular reflection occurs at a specific angle, while diffuse reflection scatters light rays in many angles rather than just one. This behavior of light in reference to other objects results in a wide variety of applications that are often overlooked as unimportant. For example, convex and plane mirrors, to be explained later, are used in cars to help avoid blind spots. Additionally, mirrors are helpful in scientific fields and are used to aid laser technologies as well as modern televisions, which utilize microscopic mirrors in order to produce clear and vibrant images. In this tutorial, we'll focus on specular reflections as well as how they work, different types of mirrors, and their important applications.
The fundamental piece behind understanding mirrors is what are called ray diagrams. When we look around, what we see isn't exactly our surroundings. It's our eye's interpretation of the light that bounces off of them. Ray diagrams help show the direction of light reflected off of a mirror, indicating location, size, orientation, and the type of viewed objects. And type meaning real or virtual, which we'll discuss a little later. When light bounces off a mirror, the angle that the ray creates to a normal to the surface is the incident angle, and the angle at which it is reflected is the reflected angle. Before delving into the three types of mirrors, we need to understand the first law of reflection, that these incident and reflected angles are always equal, regardless of the shape of the mirror. This explains very simply how to draw ray diagrams for smooth planar mirrors. Starting at the point of the object, draw a ray from it to the mirror. Then, at whatever angle it is to their normal, it's reflected back at the same angle. Concave and convex mirrors, however, are a little trickier. In any curved mirror, there lies an imaginary point that, if the mirror continued in a circle, lies in the center, called the center of curvature, or C. The middle of the mirror, let's call it point A, and C connect along a line called the principal axis. Halfway between C and A, there is a point F, the focal point. The first step to tackling the ray diagram for a concave mirror is to draw two rays of light traveling from the top of the object at hand. One will be parallel to the principal axis, and one will pass through F. Wherever these two rays meet after being reflected is where the image appears. The two other laws of reflection that apply to concave mirrors are that A, any ray parallel to the principal axis passes through F upon reflection, and B, any ray passing through F reflects to become parallel to the principal axis. So if we draw the two rays from the top of the object, wherever the two reflected rays meet is where the top of the image is. If we assume the object's bottom is at the principal axis, objects beyond C yield images between C and F that are inverted and reduced in size. Objects at C are inverted at C without size change, and objects between C and F yield images beyond C that are inverted and larger. Convex mirrors also use the two extra laws of reflection, except that the image seems to be where the reflected rays' opposites converge. Here's a visual representation that'll clear it up. As you can see, The closer the object is to the mirror, the closer and larger the image is. Convex mirrors always yield images that are upright, smaller, and behind the mirror. This behind the mirror effect that happens when light reaches our eyes that appears to come from a real object, but there's actually no object where we think light is coming from, creates what is called a virtual image.
Mirrors can be applied to the scientific field of astronomy. They are used in reflecting telescopes such as the Hubble Space Telescope, which is a type of telescope called a Cassegrain reflector. It has a primary mirror, a secondary mirror, and data collecting instruments that can capture light to create an observable image. The telescope collects light with a primary mirror, which is a concave mirror that focuses and reflects light to the secondary mirror. The secondary mirror is a convex mirror that reflects the light back through a gap in the primary mirror that leads to the data collecting instruments. This allows researchers to create images with light collected from outer space. The other main type of telescope is called a refracting telescope, which uses lenses instead of mirrors to focus light from outer space. Compared to a reflecting telescope, one disadvantage of these telescopes is that the lenses may reflect some of the light that was meant to travel through, causing the final image to be more faint. Another disadvantage is that the lenses must be larger to improve the magnification of the image, and the accuracy of larger lenses is more difficult to achieve. Also, refracting telescopes have the problem of chromatic aberration, meaning the lenses may refract light at inconsistent angles throughout the lens and result in a blurry image. Refracting telescopes are also more expensive than reflecting telescopes, so in these aspects, the reflecting telescope is superior. But the disadvantage of reflecting telescopes is that the arc of the mirrors must be very precise to form an accurate image of space. Since they are often exposed to open space, they also must be cleaned from time to time. In addition, both reflecting and refracting telescopes only work at night, and then only if the night sky is clear, or else the light from the stars will be obscured. Disadvantages aside, the Hubble Space Telescope has been very useful in observing outer space. It has given us some of the most clear images of galaxies and planets to date, and it's all thanks to mirrors.